First, for the following examples, we want to determine whether a permutation or a combination should be used. In one case, 6 students are running for student government president, vice president, and treasurer. The student with the greatest number of votes becomes president, second greatest becomes vice president, and third largest gets to be the treasurer. For our second case, 6 people are on the board of supervisors for your local neighborhood park, where a 3-person committee is needed to study the possibility of expanding the park. Where, looking at this, that first case should remind us of something we saw in the last section, because we're still dealing with treasurer, vice president, president. In this case, order matters. So we're going to be doing something in the flavor of a permutation. Remember, whenever we're dealing with a case in which we care about the way in which things are chosen, that is, we care about the order in which things are chosen, we are dealing with permutation numbers. On the other hand, for our second case, that committee is the same committee no matter who is in there first, up to obvious pettiness and egotism that comes up in those sorts of public works projects. Generally, we have to assume that order may end up mattering, but it's not supposed to matter. Really, it does to the people there, but for our purposes, it doesn't matter. And because order doesn't matter, I'm going to abbreviate that, just say combos, because we're dealing with combinations. So, if we have cases where order matters, permute. If we have cases where order doesn't matter, I want to just throw out my middle finger, choose. And choose R versus NPR is a matter of organization, like I said before, and like I will say again later. So let's get some actual computational examples in here as well to further our understanding of how this ends up coming together. For our second example, we have that funding is organized for a new scholarship and it receives 16 equally qualified applicants. The selection committee plans to accept 4 of the applicants where each will get the same amount of support. How many different combinations of 4 applicants can be selected from the group of 16? Here, we are selecting these applicants as they are. No one's going to get more money, no one's going to get less money if they're first or last. So, in this case, again, we have to pay attention to the fact that order does not matter. Where because order does not matter, and we're taking n equals 16 people and choosing r equals 4 from them, we are going to take 16, choose 4, which is going to end up being 16 factorial for all of the people involved, divided by 16 minus 4 for the remaining people who won't get funded and will have a very terrible time because we don't care about them for the purposes of this problem, and then divided by the 4 factorial arrangements within the 4 that are picked, because who cares who gets first? All 4 of them are getting the money. Show me the money! And that's really what matters here. So, from there, we can just go through carefully and deal with how these things shake out. That we have 16 factorial over 12 factorial times 4 factorial, which is going to end up simplifying down to 16 times 15 times 14 times 13 times 12 factorial, all over 12 factorial times 4 factorial, which means that we really have 16 times 15 times 14 times 13 over 4 factorial, and unfortunately, by virtue of having smaller numbers, combinations tend to not simplify quite as cleanly, quite as perfectly as what we had with the permutations, although with that 4 factorial, which I guess I should write out all the way now that it's by itself, 4 times 3 times 2 times 1, the 1's irrelevant, the 2 can cancel with the 14 to get a 7, the 3 can cancel with the 15 to get a 5, the 4 can cancel with the 16 to get a 4, which would turn this maybe into something more like 4 times 5 times 7 times 13, which looks really dumb, but will get us a value here of 1,820 total options, total combinations, total selections for the scholarship, where I should also mention here that when we're dealing with these problems, going through by hand in this way isn't the only way we can get there. As we had factorials in the calculator, and even though I didn't explicitly mention it, permutations in the calculator, we also have combinations for being able to do this sort of thing as well, depending on the type of calculator. But really, it's not that bad to do this by hand. You just have to be careful about what you put in there when. So let's get one more, maybe more advanced example to finish off this week's material with. In September of 2020, the U.S. Senate consisted of 53 Republicans, 45 Democrats, and 2 independents. How many distinct 5-person committees can be found if each committee must have 3 Democrats and 2 Republicans, where the Republicans will be the chair and vice chair of the committee? And what we have to do here is recognize we have 2 selections we have to make, which are both actually of different types, and then we have to deal with stuff in terms of the fundamental counting principles. This is a good one to end the week on because it touches all of the bases, one from each of our sections, really. So the first thing we can think about here is what goes on with the Democrats, where for them, we want N equals 45 total sitting senators, along with R equals 3 choices, where that R equals 3 is not a selection of choices where the order matters. They're just 3 members of the committee. So we have N equals, I don't know why I put an N there, I just wrote it anyway. It's a long day for recording, even though it's a short day of recordings. 45, choose 3 total options, which will end up being, in this case, I'm going to skip a half step of writing that out, 45 times 44 times 43 times 42 factorial over 42 factorial times 3 factorial options, where you get the 45 factorial from that. The 42 is the n minus r, and that's your remaining r term, where some of these cancel. That 3 factorial becomes a 6, and following a little bit of extra arithmetic that you're probably going to want to let the calculator handle for you, or at least help you out with, you will get 14,190 total choices for the Democrats. Meanwhile, for the Republicans, at that point, you would have been picking from n equals 53, r equals 2, where order will matter because you're picking a chair and a vice chair. So you have 53 permute 2 total options, which ends up being 53 factorial over 53 minus 2 quantity factorial, or 53 factorial over 51 factorial. That is, well, 53 times 52, or 2,756 total options. Where it's important to note here that even though we have more total things and a permutation, we end up with far fewer options in this second case because we were picking more things in the first. When you pick more things, you get more possible selections up to a point. That deals with things in terms of Pascal's triangle and binomial expansions, but again, topic for a different class. Anyway, here this tells us our number of Democrat selections. This tells us our number of Republican selections, and I know you guys are probably sick of hearing about elections no matter when you happen to be watching this because the coverage never stops. But if we want a total number of options for this, all we would have to do is apply the fundamental counting principle. We have this number of options for our one group, 14,190, multiplied by the 2,756 for the second, which would give us a total number of 39,107,640 possible committees that could be created. Quite a lot. Quite a lot for the government to do. But that's what we got here. That's what we got for this week. Next week, we're going to be moving forward to talk about what goes on with probabilities in the context of all these many, many possible selections. So, I'll see you all in there when we get there. Have a good one till then.